What happens to our bodies and satellite systems when they leave the surface of the Earth to travel to space or visit the International Space Station? A few hundred miles above the Earth's surface is a universe full of radiation. Apart from solar radiation, X-rays, and gamma rays, astronauts and satellites are exposed to even more dangerous forms of radiation, originating from outside the solar system.
What we're concerned with for the astronauts is space radiation, which is cosmic rays that originate either from the sun or from all the stars in our galaxy, so they're called galactic cosmic rays.
Galactic cosmic rays are bare atomic nuclei, some as heavy as iron atoms, accelerated at nearly the speed of light as they hurtle through interstellar space. Our mission is therefore designed to measure cosmic radiation as it varies with altitude. In order to get the flux versus altitude variation, we propose a slow decay orbit for our 3U CubeSat, which will begin its mission at 500 km altitude and till it re-enters and burns up in the atmosphere. This presentation will cover the following aspects of our CubeSat mission. We begin by providing the main objectives of the mission, the success level, the mission requirements, followed by the various systems and subsystems of our CubeSat, including orbit and attitude control, the payload, the power budget, amongst others. The primary objective of our mission, as discussed earlier in the video, is to detect cosmic radiation and obtain the variation with the altitude. The image below shows the illustration of how the satellite decays under atmospheric drag. Any space mission also has several secondary objectives with impact on the society. We propose international cooperation, especially between university students, by using 2 ground stations based at White Sands, New Mexico, USA, and Bangalore in India. The mission will also enable us to verify the on-orbit usability of several off-the-shelf components which we will be using in our CubeSat mission. Lastly, the mission will serve as an excellent medium for educational outreach by involving high school students and university students in the design, construction, and operations of CubeSat. We define our success level in 3 basic stages. Minimum, which entails us inquiring the technological capability of building and operating CubeSats. The survival of a CubeSat in the launch environment and subsequent reception of signals will be considered as mission success. Once we are able to verify the functioning of our payload and reception of data of cosmic radiation flux versus altitude, we can then term our mission as an advanced success. We choose a 3U CubeSat for this mission after careful consideration of the payload weight and power budget which will be needed to accomplish our goals. The mass therefore will be required to be less than 3 kgs with a side length of 30 by 10 by 10 centimeters. As discussed before, we have 2 ground stations to ensure redundancy and promote international cooperation. We will also need to ensure that the structure of a CubeSat is compatible with the Poly-Picosatellite Orbital Deployer or PPOD, which, as the name suggests, is used to deploy the CubeSat in orbit. Due to its light weight and good thermal properties, we plan to use aluminium 7075. We'll also need to ensure that the payloads are non-operational during launch and are vibration tested as well. The orbital elements of our CubeSat are strongly influenced by our primary objective. Since the driver of our concept is the inward spiral through orbital decay due to the atmospheric drag, we initialize our orbit at 500 km, an altitude with appreciable atmospheric drag. The inclination is chosen such that we get repeated ground tracks over our ground station at White Sands and Bangalore. Using STK, we also compute the average lifetime of our CubeSat and the variation in eccentricity due to drag and other perturbations, which is shown in the figure. The radiation detector we have chosen is the LUCID, or the Langton Ultimate Cosmic Ray Intensity Detector. This instrument was in fact built by high school students in the UK under the mentorship of Surrey Satellite Technology Limited. Not only can the LUCID detect the same radiation we see on Earth, but also the higher energy radiation that is only found in space. LUCID allows characterization of the energy, the type, intensity, and the directionality of high energy particles. It consumes a minimum of 0.9 watts and has a mass of about 800 grams. For our CubeSat, we'll have 4 deployable side panels with our solar cells. We'll order these solar cell panels from ClideSpace, who will work with our planned configuration to ensure that our panels interface with the rest of our powered cell system. Each side panel will provide us around 21 volts at minus 40 degrees Celsius. We plan to use a CubeSat EPS board designed for use with the 3U CubeSat. This board is rated up to 12 watts and will be able to interface with our panels, batteries and other subsystems. Our EPS board will take the power from our solar cells and do the necessary conversions to provide power to our subsystems and charge our lithium-ion batteries, so that even during the eclipse we will have power. The following table presents the power budget for our CubeSat. In a communication subsystem, the S-band patch antenna features a wide beam width that ensures satellite communications from low elevation angles without the need to point the satellite. The antenna exhibits a good input reflection coefficient which allows for efficient radiation of up to 2 watts of RF power. The STX is a compact S-band transmitter designed for CubeSat missions. It implements modulation with transmission data rates of up to 2 Mbps, which makes it ideal for space missions where a high data rate downlink is needed. The CubeSat ground station for CubeSat represents ground station solution based on high quality components designed to last, be user-friendly and to meet the mission requirements. It features a PC controlling the radio itself and a total of 4 circular polarized Yagis with independent azimuth and elevation control. For our command and data handling subsystem, we'll be using an ISIS onboard computer. This subsystem is the brain of our CubeSat and will handle the data that we collect and interface with all of our other subsystems. Our onboard computer will have 32 MB of RAM and will require about 400 milliwatts of power to operate.